Suppose you have an unlimited number of tries to succeed at something. Let x be the number of attempts required before the first success. If the probability of success on an attempt is p, then if it takes you x equals n attempts, you failed n minus 1 times, but succeeded on the nth attempt. Assuming the probability of success on any given trial is independent of the success on any other trial, this gives us our probability. This motivates the following definition. Let x be the number of attempts required before the first success, which occurs with probability p. Under the assumption that the probability of success on any trial is independent of the probability of success on any other trial, x is a geometric random variable, where our probability is given by. For example, suppose you roll a fair 20-sided die repeatedly until you get a 20. What is the probability it takes 5 rolls to get a 20? So note that our trials are independent, with probability of success 1/20, so the number of trials required is a geometric random variable. We have our probability and the number of trials, and note that this means the first 4 rolls were not 20s, which occurs with probability, while the 5th roll was a 20, which occurs with probability. Since these events are assumed independent, the probability that 4 non-20s were followed by a 20 is, or let's find the probability it takes more than 10 rolls to get a 20 on a 20-sided die. This is the same as the probability that the first 10 rolls are non-successes, so we could compute the probability as 1 minus p to the 10th, which will be but a useful strategy when learning math is to solve it again, find a different solution. So instead, we might note that the probability that x is greater than 10 is the probability x is 11, 12, 13, and so on. In other words, it's the sum of the infinite series whose terms are the individual probabilities. Using our probability 1/20 gives us, we'll remove that factor of 0.5, and we get a geometric series, which incidentally is the reason this is called a geometric probability, and we can find that sum, and we get the same answer. Now imagine coming into an experiment partway through. The probability an event occurs might change depending on what happened before. For example, let x be the number of trials that you observe before a success is obtained, but there might have been trials before you began observing. And so the important question is, do you need to know what happened in the past to determine what will happen in the future? We can view our probability as a probability that you will observe k more trials, but you might need to know how many unsuccessful trials had already occurred. For example, if x is the number of cards a person must draw from a standard deck before drawing an ace, the probability that you have to draw 5 cards depends on how many cards you've already drawn. On the other hand, if y is the number of times a fair die must be rolled before you get a 20, the probability it takes 5 rolls doesn't depend on how many unsuccessful rolls you've made. We'd say that random variable y is memoryless. We could say that random variable x has memory, but no one ever does. Intuitively, we'd expect geometric random variables to have the memoryless property. But let's prove it. We'll go through a proof for 2 reasons. First, if I don't prove something occasionally, my mathematician card will be revoked and my stand-up career is not yet a reliable source of income, and proof reviews concepts, reveals insights, and raises new questions. First, we need to identify what the memoryless property actually tells us. Suppose we observe a geometric experiment. The probability it takes k or more trials before a success is the probability that x is greater than or equal to k. But if we begin observing in the middle of the experiment, then there is some number n of unsuccessful trials. So what we're actually looking for is a conditional probability that x is greater than or equal to k plus n, given that x is greater than n. But in probability, it's useful to remember that you don't need to start with equality, but don't forget about it. And it turns out that it'll be easier to find the inequalities. So let's find the probability that x is greater than k plus n, given that x is greater than n. And remember, concrete doesn't hurt. Suppose we want to find the probability we'll observe 3 additional trials, but 5 unsuccessful trials have already occurred, so we want the probability of more than 5 plus 3 trials, given that there are more than 5 trials. Consequently, we want to prove, or not, that this conditional probability is the same as the unconditional probability. So our formula for a conditional probability requires us to find. So the probability that x is greater than n is the same as the probability that there were n unsuccessful trials. So that probability will be. Note that the compound event x greater than k plus n and also x greater than n is just x greater than k plus n. And this means there were k plus n unsuccessful trials, so our probability is. And we can simplify that quotient. Meanwhile, the probability that there were more than k trials means that there were k unsuccessful trials, and so that will also be this amount. And so our two probabilities are equal. Consequently, the geometric distribution has the memoryless probability.